Hello, welcome to another day. So I want to continue on with the simple weighted attention mechanism, but then I started thinking about um, fitting in discussion of why would you even use one of these like Tenstorrent cards. So far, it looks like everything that we've been doing has worked just fine on the CPU. We haven't done much hardware stuff except for matrix multiplications. Now, um, this is because the scale of the work that we're doing is small, so we can't really fully appreciate what the Tenstorrent hardware really brings us. And so I want to spend a little bit of time, or maybe just like kind of make the theme of this video um, kind of motivation as to why we would want a Tenstorrent um, hardware accelerator or any other like hardware accelerator or just hardware acceleration in general for this type of work. Okay. Now, want to go back and kind of show you what system I'm working on. LSCPU. Okay, so is this big enough? Here's the system that I'm currently. Wait, that's not right. Start over. So I'm SSH'd into my development computer with the hardware accelerator in there. And I want to show you the type of system that I'm currently working with. So if for anybody who wasn't following my computer build a couple videos back, I'm basically running a 13th gen Core i7 13700. It has a total of 16 cores, where 8 of that is like the performance cores, and then another 8 is for efficiency cores. Now, that doesn't really totally matter. What is really important here is basically the feature set of the CPU. So, with a lot of the work that we do a lot of matrix multiplications. We do a lot of math on the matrices, tensors, whatever. Okay, and so it starts to become more important that your general CPU has to be fast at that, since we're processing large amounts of data. Okay, up until now, we've only been multiplying small tensors at a time on CPU and then comparing that with our, I guess, hardware accelerator using TTNN. And since it's really small, you can't really see the effects. Okay, but here I want to show you that we don't have anything that is quite like modern to help us with matrix multiplications and matrix operations. Um, that specific capability I'm looking for here for the CPU is AMX. So if you don't know what AMX is, Intel AMX. Okay, so Intel AMX is what we call Intel's Advanced Matrix Extensions. Basically, it is a set of extensions that accelerates AI operations, and a lot of AI operations is basically matrix multiplications, right? Um, Literally, like I don't know if you've noticed, but a lot of it is just map moles. Like, even like linear transforms, right? Like if you look at torch linear, for example, like a torch linear is just basically y equals your input times the matrix A transpose plus B. So you're doing a lot of this stuff all the time, and so you need some sort of hardware acceleration to make that faster. Because if you ever coded matrix multiplication on CPU before, actually over time it gets slower, and it's hard to code an efficient one, right? Like a naive implementation is like a O of n cubed operation. Anyway, AMX is a hardware acceleration extension for Intel CPUs that exists in, I believe, newer Xeon CPUs. That means Intel Xeon starting from the 4th generation, which is Sapphire Rapids. And I actually have one of these, and it is really fast, like really fast. I have a 4th gen and a 5th gen, or at least I played with a 5th gen. Yeah. Anyway, super fast. No kidding, kind of like it's very helpful to have. Okay, and the basic architecture is outlined in this product brief here, but what I'm trying to say, and rambling, is that the 13700, the Core i7 13700, does not have the AMX capability. Now, what does that even translate to, right? So, like, if you look at the Tenstorrent wormhole, okay, so if we look at the n150d, for example, okay, this is the exact same card that I have in my computer. So if I were to start this environment and do TTSMI, I see that I have an n150, okay, in the system, in this development system. And so, and then when the D and the S just kind of indicate the specific type of cooling. So what I really want to focus on here is not the number of cores, not the clock speed, not the L1 cache, not the memory or the memory bandwidth. All that is important. But what really sets us apart is basically these numbers here. Okay, the number of T-flops, teraflops for specific data type calculations. Okay, so with the n150d, okay, the Tenstorrent wormhole n150d, what it can do is up to 262 trillion floating point operations per second on FP8, 74 trillion floating point operations per second on FP16, and then 140 trillion floating point operations for bfloat 8. Okay, so let's just take this one. This one's very common and popular, right? So FP16, okay, 74 trillion, 74 teraflops per second, just for this specific piece of hardware, with a total board power of 160 watts. And spoiler alert, I haven't even gotten to use 160 watts worth of power yet. So this is what makes it even like more motivating. Okay, is that it doesn't really use that much power for basically 74 teraflops. Okay, so then you're like, well, okay, you have 74 teraflops of worth of compute. Okay, 74 teraflops. What about our CPU, right? The Core i7 13700. Okay, so let's see how that compares to just pure CPU compute. So if I look at Intel Arc, right? I don't even know if it even shows me this, but basically, I can consume up to 219 watts of power full tilt just for this thing. Okay, now memory bandwidth here is just basically, this is actually really at pretty much DDR5 5600 megatransfers, right? I'm on 5600 megatransfers, so it is about 90 gigabytes per second. I haven't even measured, but I'll trust it. Okay, here we go. So we have advanced technologies, right? So all these accelerators and all these things. Okay, we have AVX2, but not much else. So what is actually the number of teraflops that this CPU can do? So let's look that up. Okay, so I did some research with trying to find the estimated floating point T-flops of a Core i7-13700. I had to tap into Gemini to do all this math for me. At first, it gave me the results for the iGPU, which I wasn't really interested in. So I went ahead and kind of just have it drilled into just the CPU itself, and this was actually the result that it gave me. So I'm going to read. I'm going to read this. So it's important to distinguish that the previous TFLOPS estimation was for the integrated GPU within the Core i7-13700. So I knew that. That's the reason why I said, okay, let's clarify. Estimating the FP16 T-flops for the CPU cores themselves involve a different set of parameters. So, okay, so this is a rationale, how to calculate T-flops, right? Here's a breakdown of how to approach the CPU FP16 T-flops estimation for the Core i7-13700. Core specifications for the Intel Core i7-13700. So basically we have 8 P cores. It cranks up to 5.1 gigahertz. We also have 8 E cores, which goes up to 4.1 gigahertz. Now, Gemini makes a point saying that, okay, we support Intel SSE 4.1, 4.2, and AVX2, but there is no AVX 512 support, and there's no Intel AMX extensions, as said before. So this one is important, but only found in Xeon CPUs. Next, let's get to the real purpose of this question. FP16 operations per cycle using AVX2. AVX2 instructions operate on 256-bit or 32-byte registers. So we have 32-byte registers. For floating point 32, an AVX2 FMA fuse multiply add instruction can perform 2 operations, a multiply and add, on 8 floating point numbers simultaneously. So 256 bits divided by 32 bits per floating point number gives you 8 floats. So with 8 floats times 2 operations per float gives you 16 FP32 flops per FMA instruction. So this benchmark is against the FMA instructions, the fuse multiply add instruction. So one core can execute 1 to 2 FMA instructions per clock cycle. Cool. But what about FP16? So using AVX2, things are a bit more nuanced, as AVX2 doesn't have direct full throughput FP16 FMA instructions in the same way AVX 512 does with its specific FP16 support. However, AVX2 can be used to process FP16 data, often by converting to FP32 for computation or using specific instructions if available for packed FP16 operation. So this means that actually when you have an FP16 number, that gets upcasted to an FP32 so that we can do all this stuff here. Okay, so then you don't get the same throughput as dedicated FP16 units as with GPUs and AVX 512, or even our friend the n150d. Okay, so there are some AVX2 instructions that can handle packed FP16 data. Okay, basically this instruction here converts 8 FP16 values to 8 FP32 values. So if we assume that FP16 operations are effectively processed using the FP32 execution paths within AVX2 units on these cores after conversion, or that specific packed FP16 instructions yield a similar number of operations on a 256-bit vector width, a 256-bit vector can hold 16 FP16 values. Okay, so this is trusting Gemini. This is like at a very good case, right? We're like being very optimistic here. We're being able to pack these FP16 values as FP16 into 16 different values. So let's say now we're saying, okay, we're going to have 16 floats, okay? So an FMA like operations could sustain 2 ops. This would mean that we have basically 32 floating point 16 flops per cycle. Okay, now knowing that we have 32 floating point 32 well, this should be actually 16, but right here. Floating point 16. Let's just go here. Okay, so we have the ability to process 16 floating point 16 numbers per FMA unit, 2 FMAs per cycle, times 16 flops per FMA times 2 ops is basically 64 floating point 16 floating point operations per cycle per P core. So there's 8 of these, so it's going to be 8 times 64 per cycle. Now we also have the E cores, same type of math, but you get 32 of those. Okay, and you have 8 of those, so it's 32 times 8. So now the at full tilt at 5.1 gigahertz, all core full tilt, okay, we're able to achieve basically 8 times 5.1 gigahertz times 64 gigaflops, which results to 2.6 teraflops. Okay, teraflops of FP16. And again, Gemini is calculating theoretical peak. With the E cores doing the same math, we get 1 teraflop. Okay, so that totals up to about 3.6 teraflops with both the P cores and the E cores going at full tilt. So full tilt, again, if we went to Intel Arc, I think, what is it? So at full tilt, we're like 219 watts of power versus the 160 full tilt for our Wormhole. But again, I have yet to see that. So 3.66 teraflops FP16 operations for 13700. But again, there's considerations, right? Because like we're assuming a lot of things here. Gemini is just being very optimistic. So let's just assume it's anywhere from like 2 to 3.66 teraflops for FP16. But remember, our n150d can do 74 of these at a lower power envelope. Okay, so what was all this for? What I'm trying to say is that the hardware accelerator, especially what Tenstorrent is trying to achieve, is scale out. So the whole point is to be able to pack a lot of these in a data center or in a machine and perform inference at a very efficient, or at least a very power efficient manner. You have GPUs that actually use more power than this and that cost a lot more. And if you don't have that type of, economic resource, this is a great alternative to not only be able to get somewhat close to that same level of compute, but at a very good power efficiency. So if the work that you're doing involves a lot of FP16 calculations, you could fully take advantage of that hardware acceleration and get a very efficient system going. Doing it on CPU is much harder because depending on what kind of CPU you have, you may not have the same type of hardware accelerations. Of course, like something like the Xeon scalable CPUs, maybe the higher end ones, they are going to, of course, not only cost more, but then it'll take a lot of money just to achieve this same number of floating point operations per second. So this is like what I actually want to inform everyone about, so that we can stay motivated in what we're trying to do here. So today I'm going to show you some benchmarks in some of the operations that we're doing with like CPU and hardware accelerators, to just really show you the difference, and maybe I'll probably get down and take like a picture of the power consumption that the computer is using while it's performing all these multiplications and transformations and all that stuff with matrices. Yeah. All right, so I'm good rambling now. I hope I've made some of my point go somewhere. All right. Let's start a new notebook, and let's just write. Let's generalize our simple weighted attention mechanism, and then go from there. So, 07 simple weighted attention mechanism v2. Goal is to create some reusable code here. We might be reusing some things for our multi-head attention mechanism. And we're going to use this notebook as an opportunity to do some benchmarks. Okay, let's do it. So first we're going to import some libraries. So again, import torch is what we pretty much always need. We'll also need the import nn. Okay, so torch.nn. And then let's set the manual seed to 789. So going back to Sebastian's book here, his book notes, I think he did use 789 at some point. What is it? 789. Yeah. Yeah, right here. Okay. So we're going to basically create like a reusable version just like this, but using TTNN. So gotta get started with that. So next step is we're going to write that same class. So I feel bad for like just copying it, so I'm just gonna type it and try to like explain it so that I feel less guilty. It is from the book, so and it is in GitHub. And you know, again, go to LLMs from Scratch repo if you want to know more. So all right, class self attention v2. I think that's what it's called. Let's just do it this way. It's going to inherit nn.module. Okay. And then we're going to do def init self din dout super.init. Okay. Then inside this class, we're going to have 3 attributes. Again, it's going to be the query, key, and value trainable weights. They are going to be linear layers in Torch. So we do self query is going to be a new linear layer with din, dout dimensions, and we're not going to have any bias. Same thing with key, and then dot linear, din, dout, and we are not going to have any bias. And finally with value, and then dot linear, din, dout, bias is false. Okay, we're going to specify a forward pass, and it's just going to apply those linear transformations to get the key, the query, and the values. So, and I'll explain what that is actually doing once I type all this. So this is against taking the the matrix X coming in, multiplying basically by not multiplying, but performing a linear transformation against these matrices. So, okay, I'll pause right there, and I'm going to flip back to documentation. So going back to the PyTorching, when we do this, so what we're doing here is we're taking this input X, and we're performing the linear transformation against these weight matrices. So if we go back to here, we'll see. Oh, whoa. Hold on a second. Okay, yeah. So we'll see this operation here. This is X, and this is the weight matrix. So we need to transpose that weight matrix and multiply that against X. And here, what this torch module does internally is that it's going to do that transpose multiplication against the X. Yeah, so that's what it's doing. And what we can do now is we can calculate, again, attention scores. Then we're going to scale normalize that. Then we're going to calculate attention weights by normalizing that resulting scaled attention scores. Then we'll get the context vectors. So we're going to do all that inside this for pass here. So we're going to get attention scores. That's ATTN scores. ATTN scores. That's going to be the queries matrix multiplied by the transpose of keys. So keys.t. Key.t. Yeah, key.t. Why did I say key? It should be keys. Okay, so keys.t. Then we are going to normalize the attention scores, or scale them first. Attention scores scaled, and that is attention scores divided by, in this case, we want to take the dimensions of D out, and that's equivalent to basically the dimensions of these things here. So we could just say keys.shape -1 square root, so that's going to be to the half power 0.5. I think I should just do it like this so it's easier to read. And then we are going to calculate the attention weights, which is the softmax of the attention score scaled on the last dimension. So that's going to be torch.softmax attention scores scaled. Dimension is going to be on the last dimension, which is -1. Very Pythonic way to do it. Then we'll calculate the context vex, and that's going to be the attention weights matrix multiplied by the values, as what we were doing before, and we could return the context vex. So that's what we're trying to achieve with self-weighted attention. Okay. Yeah, so let's try it out. Again, we're going to need our inputs, which is going to be, in this case, the same context that we used last time. I'll just copy and paste that here. Okay, there we go. Okay. What's going on? Oh, I need to select a kernel. Okay, there we go. Okay, let's do it again. It wasn't doing that this whole time? That's weird. Okay, so, again, that's right, 6.3. And let's now actually run the self-attention mechanism against our context. So we can define a dimension, dn. That's just going to be context 0 dot shape maybe 0. Then d out is going to be context 0 dot shape 0 as before, d in, d out. 33, we're going to create our self-attention mechanism. So self-attention v2 with d in, d out, and that's in the constructor. We define that to take in, what is it, d in, d out up here too. So same thing. Okay. What we want to do now is we want to grab the context vex based off of the input by passing it into our self-attention mechanism. And then let's actually output that too. And we get numbers. Okay? So how we know that this is correct? Not quite yet. It's still kind of nonsense because it's not trained correctly. But a good way to check in the future is to port this over, everything that we just did right now, to TTNN, and that's what we're going to do. So let's start writing some notes here. We'll say simple weighted attention mechanism v2. Okay, and then let's do torch implementation. Okay, and then now let's add TTNN implementation. So this is going to be using our hardware. We're going to port what we just did right now to TTNN, and assuming that we're still new to this, let's port it over the most naive way possible. Okay, so we're just going to directly translate all of this in that we're going to create a new class. We're going to translate all of these operations to just using TTNN with what we currently know. First things first, let's import TTNN and also define our device ID and grab a handle to the device. So we're going to open the device again. And we can do just that with TTNN open device with device ID, device ID. Okay. And if all goes well, we should see that log that we're also familiar with saying that the chip initialization is complete. Great. Okay. So let's think of our approach and let's just write down the notes here. Okay. The goal of porting over our torch self-attention v2 class is to translate or is to port the implementation over line by line to TTNN, like I said before. So what does this involve? So let's consider this line here. So this line of code, okay? So we'll wrap this line of code. In this case, we had our attention scores, for example, where we took the queries that we computed from our linear transformation of the W query with the input passed into that. Okay, and then we to get the attention scores, we took that result and we did a matrix multiply on the transpose of keys, which is a result of passing our inputs to the weights of keys. Okay, now suppose we have that line here. Like, what would a TTNN port involve? So porting to TTNN would involve basically, in the naive way, let's just say this, in the naive way, okay? So knowing what we know, we only know a few basic things. We know TTNN matmul, we know TTNN softmax, we know how to move things to the device, we know how to change layouts. Like, this is as much as we know. So knowing what we know, what can we do? Well, at the torch level, okay, when we're in Torch, we can assign queries to be the result of the linear transformation of with W query. Okay. Do we call this linear transformation? I've been using this a lot. I wonder if that's even the correct way to say it. Let's see. Yes, linear transformation. Just making sure. I'm still new to this. Okay. All right. Next, so we assign queries to be the result of the linear transformation with W query. So again, if you remember the code, it was something like queries equals W query X pseudocode wise. Okay. Now again, staying at the Torch level, we transpose the keys. Okay, the keys result of linear transformation with W key and X. Okay. So we transpose that result, and we'll call this we'll call this keys transposed. Next, we're going to be at the TTNN level now. So we're going to do things in TTNN. We have these two things here. We have the queries and we have the keys transposed. So what do we do that? What do we like? How do we use TTNN for that? So we can create the TTNN tensors from queries and keys transposed. So what we're trying to do now is, given this result that we did in Torch, given this result that we did in Torch, okay, we're just going to create TTNN tensors off from these two things, off from queries and keys transposed. So what we get back is we're going to get back queries TTNN and keys transposed TTNN. Okay, so bear with me. I know, like, the really smart people that are watching this are going to go, why are you doing like the same thing twice? Because you're already doing a CPU operation on Torch, and then you're gonna do this again on hardware. Are you? Well, just stick with it. Okay, so at the TTNN level, we're gonna compute the multiplication of the tensors using TTNN.mapMul, and the tensors are queries TTNN and keys transposed TTNN. Since there is no bias, we don't have to worry about this. Okay, so that's going to be the approach. Okay. Okay, so let's write the code. And we're not going to write the class just yet. We're just going to take those set of operations that we've just discussed here, and we're just going to translate that into code. So remember that we had our SAV2. Well, we can just access those attributes, like these attributes. Where is it? These attributes here directly, right? We could do like sa.wquery, sa.wkey. So we'll just do that real quick, just for demonstration. Okay, so this is the Torch version. Okay, Torch operations. So we'll have queries is going to be sav2.wquery. We can access that because sav2 is an instance of self-attention v2, and self-attention v2 has the w query as a property. So we'll throw our context into there, and context was all of this here, right? So we'll throw our context in. We'll also compute keys, which is what we need. Same thing, w keys, and then context. So wait query, wait key, and then input in. Then we also want to transpose the keys. So we just do keys.t. That's how we do that in Torch. Okay. Now, so we did these two steps, first two steps. So steps 1 and 2. Okay. Now we'll have ttnn operations for steps 3. Okay. And that's going to be queries ttnn. It's going to be ttnn.from torch. So we're going to create ttnn tensors from torch using queries with dtype ttnn.bfloat16. Layout is going to be ttnn.tile layout, and device is device that we are currently using. So again, this is basically performing like we're gonna be doing like the operations twice essentially, because the memory here is not shared. Like this tensor is going to be a different copy, because this is actually a torch tensor that is floating point 32 type, while this one's a bfloat16 type. And if we go back to the documentation here, I think they call it shared memory. Shared. Actually, let's go to ttnn. And then let's search for shared memory. Tensor. Okay. So the caveat here is that usually there's a detail about this. Shared tensor. I forgot the term, but let's see, memory config. No, it's getting started. Explore tensor, layout, shape, data type, blah blah blah, storage. Okay, it's storage. Okay, so there's borrowed and then there's owned. So I think we're looking for borrowed, right? Borrowed storage. Okay. Okay. So host storage, borrowed versus owned. In this particular case, ttnn tensor will borrow the data from the torch tensor, because ttnn tensor is in row major layout and the torch tensor is contiguous and their data type matches. So borrowed storage. Okay, so we are not using borrowed storage, and borrowed storage, going back, is the buffer of the tensor is on the host and it was borrowed from torch, numpy, or an external buffer. So there's a demo of this showing that it's the same tensor, right? But in our case here, since the data types are now different and the layouts are different, this is a completely new tensor. So that's the reason why I say you're like kind of repeating the same thing again. So let's also convert keys transpose to be a ttnn tensor. Okay. And now we need to do step 4. So step 4 is a mapmol, right? It's a mapmol. So now we need to do step 4, which is the ttnn mapmol to find the attention scores, and we want to get that ttnn version. So it is just queries ttnn and keys transpose ttnn the multiplication of that, we're basically trying to simulate this here. So we have already transposed, and we already have our context, and we don't have a bias. So it's just a simple matmul here. So we could say attention scores, ATTN scores is queries, ttnn.matmul, and I should probably suffix this with ttnn. Okay, so matmul queries ttnn and keys transpose ttnn. Okay. I think we also want the CPU version of this too, so that we can do a quick comparison. So let's do that too. Compute the torch version 2 for comparison. Okay. Attention scores. There's just no suffix. It's just actually, yeah, let's do it. Torch. So we can remember. That'll be queries, which we have up here, and we want to matrix multiply by the transpose. And let's return back both the TTNN version and then the torch version. So doing that here. So we look very close to a few of these. We do get close. So this one is the TTNN version, and this one is the torch version. And yeah, it's pretty close, like negative 0.22168 versus negative 0.2219. 31641 negative, right? Negative 3159. Going all the way down, you see negative 0.2371, negative 2373. All the way at the end here, negative 0.21484, negative 0.2134. Pretty close. So, yeah. Now, let's go even further with what are the next steps, right? Well, we have our attention scores. Now we need to scale them and normalize them to attention weights so that it all adds up close to 1. We'll check that too with our TTNN version. So again, the operation that we're trying to translate. So now the operation that we are trying to translate from torch to TTNN will be, okay, Python, I'm going to do this from memory. Attention scores scale is, I think that was just attention weights. Was it divided by the keys.shape -1 times 0. or raised to the 0.5 as a square root, and then attention weights is going to be torch.softmax attention scores scaled dimension -1. Okay, I think this is what we were doing. Yes, okay. So we want to be able to translate this to TTNN. Okay. So what is the first thing to do? Well, we can first get the scaled version of attention scores scaled in TTNN. That is using maybe the ttnn.div operation. I typoed here. It's supposed to be attention scores. Okay, so we get that. Then perform a ttnn.softmax. Okay, of attention scores scaled ttnn. Okay, we should probably call the results attention scores scaled ttnn. Okay. So then you know what? Let's just go all the way. Context of x was attention. Brain fart. Was it attention weights matrix multiplied by the values? Yeah. Okay. So lots of things to remember. Okay, attention weights matrix multiplied by the values. So then, we get all the result attention weights TTNN. Then finally, we need to be able to get values TTNN by performing the transformation of W value and context x. Does it say x? Of nx and converting that to a TTNN.tensor. Finally, compute the context vex TTNN by matrix multiplication, or let's do by calling TTNN mapmul on value tension weights TTNN and values TTNN. Okay, so that is our approach. So we're going to translate this code here. We're going to get the scaled version of attention score scaled in TTNN, and that's also involved using ttnn.div on the attention scores TTNN, and also just this scalar value. Then we're going to get this attention score scale TTNN, throw that into a TTNN softmax against the last dimension, and we're also at the same time, or like right afterwards, we're going to get values TTNN by doing the torch transformation of W value and X and then converting that to a TTNN tensor. And then we're going to compute the context vex TTNN by calling TTNN mapmul on the attention weights TTNN version and the values TTNN version. Whew, it's a lot. But let's type. It should be easy now. Okay, so we have our attention scores scaled on the torch version, but we need a TTNN version scaled. So attention score scaled TTNN is going to be ttnn.div on the attention score scaled that we already found. Did we? No, attention scores TTNN on this one. Yeah. Against keys.shape -1 and then square root of that. Okay. Just for sanity, what did we get? I think that worked, right? Yeah, that worked. Okay, so continuing on, we're going to get the attention weights TTNN by performing the softmax of attention score scaled TTNN and on the last dimension. Okay, so far so good, still works. Then we need to get the values of the torch transformation. So SAV2.W value against, I think, context it was, and then we're going to turn that into a TTNN tensor with ttnn.fromTorch. And what we want to do is we want to pass in values here with D type going to be dfloat16. Okay. Layout is going to be a tile layout. And then finally device is going to be device. So we'll have the TTNN here for values, TTNN tensor for attention weights. So we have a context vex TTNN is simply the ttnn.mapmul of attention weights TTNN and the values TTNN. And let's actually also compute the CPU version. So compute the torch version for comparison. Context vex is going to be, in this case, I'm just going to try to see if I can compute it. Matrix multiplied with values. Was it SAV2 dots W value on context? So that's value. How do we do this? Torch dot soft max of what? Of actually, we already have a torch. Attention scores torch. Okay, so we want to scale that. So attention scores torch divided by keys dot shape -1 to the square root on the last dimension. I think that's the equivalent. Yeah. Okay. So we'll output context vex ttnn, context vex, and I hope they are relatively the same. Yes, they are. Great. So checking our answers again, here's our context vex ttnn, and then here's our tensor for torch. We're going to get 0.41406, 0.4155, and close. 0.41211, 0.4146, 0.4146, wow, all the way down here. It's all the same. Back down here, relatively the same. Close, right? Not same, but close. So we're doing good. We're doing good. So now what we need to do is we're going to have to put all of this together. But before that, let's close the device because I am going to forget. And let's move on to the next thing. Okay, so now we're clean. So what we want to do now is we want to create a class that kind of wraps all of this type of logic into the forward pass. Okay, so it's just writing that same self-attention v2 again, but let's call it a self-attention self-attention ttnn v2, and then throw all of this stuff inside the forward pass. So let's add some notes. Self attention ttnn v2 implementation, and then let's call this the naive way, because that's what we've been doing. We've been doing the naive way of this. Okay. So let's write that. What is it? Class self-attention v2. Nope, not v2. ttnn autocomplete. Just getting too used to it. Okay. Class self-attention ttnn v2. Again, still, but still a torch class. It's just that underneath the hood, when we do the forward pass, it's just going to use our hardware. So maybe I should write that down. This is still going to be a torch module. It is just that now when we do a forward pass, we will be using our accelerator, the Wormhole n150d. Okay. So I think initialization is going to be the same with the constructor. But this time we're going to pass in the device as a property, because we need that to tap into our accelerator and perform those operations. So that is the reason why. So we'll draw super init because it inherits from nn.module, and then we'll just define our weights, the query weights, the key weights, the value weights again. They're linear modules, so same thing again with no bias to make things easier. WP is nn.linear, dn, d out, bias equals false. Then self dot w value is n.linear, d in, d out, bias is going to be false again. Okay, so we've defined the same thing as before, but now we need to also maintain a device instance variable. Okay, so that when we do the forward pass, we can actually use our device. So self x, and I'll pass for now. Okay. Okay, so let's continue with that forward pass, and again, naive way. So let's just compute the the keys, queries, and values using the torch way for now. Okay, so keys is going to be self dot w key x. I laugh because this is not good. So queries is self dot query, and then value is going to be self dot w value. Okay. So we'll have these tensors, but they're still in torch mode. Well, torch mode, CPU mode, right? And so we'll just convert them to TTNN tensors. TTNN dot from torch. So that's going to be queries in this case. D type is going to be TTNN dot b float 16. Layout is TTNN dot tile layout. And then device is going to be self.device. So we're maintaining the device as an instance variable. We'll just use self.device here. So that's why we need that. That's why we need this instance variable, because we have to do stuff like this where we need to tap into the current device. Okay. Now, yeah, we'll just again do it for the rest of these things here. So values, TTNN is TTNN dot from torch. Values, D type, TTNN dot b float 16. Layout is TTNN dot tile layout. And device is going to be self dot device. Okay. I don't know why I'm not want autocomplete. I don't even have a model set up for this computer. Okay, there we go. Things should feel a little faster now. I feel like when I type, there's like a little lag. Okay, so keys TTNN is going to be TTNN dot from torch. Okay, and we're going to get keys D type TTNN dot b float 16. Layout is TTNN tile layout, and then device is self.device. Okay. We'll also need the transpose of that, so that is just using permute. So in this case, keys transpose TTNN is TTNN.permute. We'll permute keys TTNN, and we're going to flip it with 1 0. 1 0, yeah. Is that correct? I feel like that API, let's see, permute. Yeah, 1 0. That's from our last notebook. Okay. We're going to now get the tension scores. We're also going to take that tension score, scale it correctly. We're going to then get the tension weights. Then we're going to get the context vectors from all that, and we'll return it. So one thing at a time, and we have to do this all in TTNN. At this point, we do have enough to just do that. So attention scores, TTNN, for example, is just basically going to be the mapmul of queries and the keys transposed. So TTNN.mapmul is going to be queries, TTNN, and the keys transposed TTNN. Then we have attention scores scaled TTNN, and that is the math we did earlier, TTNN.div on the attention scores TTNN. And then also, in this case, we can say keys ttnn dot shape -1 square root of that, and then we'll find the attention weights ttnn by performing the softmax of the attention score scaled ttnn on the last dimension. Okay. Finally, context vex ttnn is the ttnn mapmul of the attention weights ttnn and the values ttnn. And for the sake of compatibility, we should just return the torch version of context vex ttnn. So context vex is going to be ttnn.toTorch context vex ttnn and return context vex. So this makes it more transparent that what we get back from this forward pass here is going to be still a torch tensor, but all the math is done with ttnn. And we used everything available here that we declared. So in this case, keys, queries, values, torch becomes queries, keys, values, ttnn. Then we take the transpose of keys ttnn to get keys transpose ttnn by using ttnn.permute. We get the attention scores ttnn by performing a map mul on the queries ttnn and the keys transpose ttnn. We scale that with this scaled value here. We perform the softmax for the attention weights. Then we do a map mul against the attention weights and the values, ttnn version. Then we transfer back to toTorch, and then we return our final result. Okay. Looks like it worked on the first shot. Okay, so let's test it. So we need to open up our device again, and we need to create a new instance of this specific class here, and then we'll just perform a forward pass with the context, and we'll see what we get back out of it. And what we get back out of it from the forward pass is going to be a torch version of the context vex. Okay, so device ID is 0 again. Get the handle to the device. Device ID is device ID. Okay, and then we already know what the context is, so we also know what D in, D out is. So we'll just create a new SAV2 TTNN or SA TTNN V2. And then it'll be self attention TTNN V2 with D in, D out, and then also the device that we have. And then we'll forward pass context vex SA TTNN V2 with our current context. ttnn.close device, and then let's just print out the context vex. We can do this after we've closed the device because this is actually not a torch, or this is not a ttnn tensor now. It's a torch tensor, meaning that it lives on CPU. So here we go. Okay. So we get 0.177, 0.1758, and so on. Okay, so this looks weird to me. This looks weird in that we don't have the same answer as before. When we had computed this manually, we got close to the same answer. So why is that? Why is that? Is it because we didn't set the manual seed? Let's see. Torch.manual seed. There we go. All right. It was 789 was our manual seed. So we got a completely set of random numbers, and that's the reason why. So again, similar as before, you know, 0.048 something should be the very last element, which we got here too. And then the second column should be all negatives here. And did we see the same thing up here? Indeed we did. So yeah, and then 0.41406 down here is 0.4141 for whatever reason. Yeah. Okay. What's next? Should we benchmark? Let's start benchmarking. Let's start measuring, because technically we're doing everything in hardware here, and it would be nice to see how that compares with the CPU version. And these are dumb, naive implementation. Okay? So we'll need a helper to actually measure some time. So let's do this. Benchmark. So let's see here. No, I don't want Copilot. Okay. So let's define how we are actually going to measure time. So it's pretty easy. And how you do that in Python is just doing import time. We'll have a start time with time.time, and then we'll do something. And then we have an end time, time.time, and then we could just print out in a nice formatted string. Time is going to be end minus start, and we could say multiply by 1,000, because I think start or time.time is in seconds, so we want to change that to milliseconds. So let's see how long it takes to print out do something. Yeah, 0.1897 whatever milliseconds. So this is about right. Okay. So let's actually define some API. We'll call it a perf timer implementation. And this is going to help us do like measurements of time. So it's going to be a simple Python class that has API to start, stop, and get the elapsed time, so that we can just benchmark things in a consistent way. So import time. So same thing as before, but this time we're going to call this a perf timer class. And our constructor is going to take in no arguments. We'll have self.startTime. We'll start that at 0. Self.endTime. We'll end that at 0. We'll have API start. That's just basically setting the start time to be time.time. And then we'll also have API stop. Okay. That's just setting the end time to something. Time.time again. And then we'll have a reset so that we can use the same instance all the time. So self.startTime is equals to 0. And then self.endTime is also equal to 0. And then we'll have elapsed time. Let's do elapsed ms to make the unit clear. That returns basically what we did the math earlier here, end minus start times 1,000. So self.endTime minus self.startTime times 1,000. So that's our perf timer class that we can use. Okay. So what we want to do is, since we forward pass against a bunch of vectors, like the context is like 6. It's like a 6x3. Was it? Yeah, 6x3 tensor. We can just create in this case like maybe larger ones and a bunch of them, and let's just like just in a loop, just throw them all in, and one by one perform forward passes against the self-attention mechanism. Okay, so let's actually create like a stack of these tensors, and let's actually time how long it takes to do that with our 13700 CPU. So let's write code for that. We'll do torch.manual seed 789, and then we'll create a new perf timer instance. Let's be more. Timer, okay? Yeah, timer, perf timer. And then we'll start here, and then let's create timer.start, and then let's create one ender, an ending one, and then let's also return back the t.elapsed timer.elapsed elapsed ms. Okay, so in between here we want to do something. We'll just like create these bunch of torch tensors. So what we're going to do is we're going to create a bunch of these large tensors, and then iterate through each one, forward passing that tensor into the self-attention mechanism, and just like once we're done with doing all of those tensors, we'll just get back to time. So we'll just need to create those first. So we'll use torch.stack and torch.rand n. So we'll just create random tensors of 1024 and 248 dimensions. And then yeah, let's do that for maybe 1,000 times. Yeah, let's do that for 1,000 times. Okay. Then let's see what we get back with torch tensors. So, oops, no, typo. There we go. Let's do it again. So that should take maybe about 10 seconds or so. Why? There's no end. It's stop. Do that again. Okay, cool. Took about 5.2 seconds. Not bad. So, let's also output the shape too, just so we know. So what a waste of compute, just doing the same thing over and over again. Okay, so 5.4 seconds for 1,000 of these. Shape is 1,000 of these 1024 by 2048 tensors. It takes about 5.5 seconds or so to create these things. Okay, so let's measure how long it takes to process 1,000 of these tensors on CPU. All right, now it's time to write the CPU version and then measure the time it takes to just forward pass all those tensors that we created up here, these torch tensors. Yeah. So let's do this. Self-attention v2 on CPU. Okay. So what do we have to do here? Well, let's first timer.reset. Let's reset our timer. Let's start our timer. And then let's now just create a new instance of the self-attention mechanism that we had for CPU. D in, D out. And then we're going to loop over every single tensor. So for tensor in torch tensors, what we want to do is we want to compute some like forward pass of this thing, giving tensors as an argument to our self-attention v2 instance. And I'm just going to keep the last result. There's no like reason. It's just I just needed to do some work just to show and then get something back printing out here. So there's no reason. You could have just like not saved the result, but just for the sake of seeing something. Lapse ms timer.lapse ms. Okay, sorry, I'm getting tired. Hard to explain stuff. Okay. let me do that again. Okay, so I'm gonna reset the timer, and I'm gonna start the timer. I'm going to create a self-attention v2 instance with d in, d out dimensions. We're going to loop through over all the torch tensors that we created earlier, doing a forward pass of the self attention mechanism by passing in the individual tensor every single time. I'm only interested in keeping the last result here to print out, but as this thing is iterating, it's always just going to reassign it for whatever reason. I don't care. Just give me something back at the end. Then we'll stop the timer when everything is done, and we'll print out how long all that took. So, ready, set, go. Oh, why? Oh, it's not D in, D out. We had, what did we have again? It was what? 2048, right? So, was it 2048? It was, we used, yeah, it was 2048, something like that. Okay, it was a 1024, 2028 of these, so 2048. So yeah, let's see how long all that takes. Okay, it's taking a while, isn't it? For 1,000, it should take maybe a minute. I've done this before, and last time it took like a minute. Okay, so it took about 56 seconds. That's with the CPU. Okay, now let's do our TTNN version, so hardware-based version, the naive way. Same type of benchmark. So let's see what we get there for those 1,000 tensors. So self-attention V2 on TTNN. And then let's again disclaim it with naive. At this point, naive should just be silly. Okay, so timer.reset again. Then we'll do timer.start, timer.end. Then we'll also want to return timer.elapsed ms. And we'll put something in between here. So let's first, after reset, let's open up a device. So device ID is 0. Device handle, TTNN, open device, device ID, device ID. Okay, now we'll have our device. And then let's, it's not end, it's stop. Let's, so that's like a sign of like a bad API naming, right? Like if you keep using a different nomenclature from what you really named it as, it might be worth just naming it to that. So that means to me end is more intuitive than stop, but it's okay. I'll get used to it. Okay, so make sure we close the device. We don't want to leave the device hanging. Okay. So SATTNN v2, we'll just create an instance of the self-attention TTNN v2 instance. I think it was 2048, and then our device is going to be device, and we're going to loop through. Since our forward pass already takes in torch tensors for this class, we don't need to change anything. It just becomes this again. Okay, so nothing really changed much except that now we're using the self-attention TTN v2 and we're hitting it against the device. Okay, so same benchmark, 1,000. Let's see what we get. Run it. So one thing to note is that whenever you open the device, it does take more time to compute. So I'm going to run this twice. So the first time it takes much longer. let's see what this looks like right now. So right now, our device is using about 12 watts, and it's using about 15. I don't know what this is. 8 amps. I don't know. So I don't think this auto refreshes. Does it? Oh, it doesn't. Okay. So we're using about 32 watts of power during all this, and this makes more sense now. 1,000 megahertz for the core clock. It was 500 before, probably for because it was idle. About 57C. But this 32 watts here is actually pretty important to know. It looks like this thing is like kind of locked at 100, and I think the 60 is probably for like the cooler, maybe. I don't know. Because paperwork says that this card should be using 160, yet this thing is locked at 100. It's okay. I mean, I'll take it. It's power savings. Okay, so this thing took about 68 seconds to finish. And that is the first time around. But let's run it again because... Oh! No, we can't because I closed the device. So, again, like I said, every time you open the device, it takes a lot longer. It takes a lot longer. And what we want is to keep the device open to run this thing. And so what I'm going to do is I'm going to split my code here, and I'm actually going to open the device here, and I'm going to close the device when I'm done. Okay? It just works differently this way. Okay, I'm going to close the device here, and it should... Where's my... There we go. Okay, I should be able to run it 2 times again, and I should... Too excited to run benchmarks. Should have just also output the result. What do I do? I'll just let it run. I know how long it really takes. About 68 seconds. So in about 7 more seconds, it'll be fine. Okay. So the device is closed again. So I'm going to open it, and I'm going to run it one more time properly. And then I'm going to come back in a minute, and then I'll show you guys running it again the second time when the device is actually warmed up. Okay, so that run took 70 seconds, but let's see what it looks like for real now. So this is when a device is warmed up, how long it takes to compute. And again, this is the naive self-attention mechanism. And we're going to do some fun stuff after this. But let's see how long it really takes. Okay, so this time it still took almost 70 seconds. This pretty much why I kept saying it's a naive way. Because the CPU actually ended up being faster than the hardware, supposedly hardware accelerated version of, the self-attention mechanism. Okay, so obviously we can do better. But why is this slow? This implementation is slow because we do several silly things in our TTNN version. First, in our forward pass, we recompute the torch version, the torch calculations here all the time. So we're actually on top of like whatever we're doing on the CPU side of things on our regular self-attention, we're actually doing it again in our TTNN. We end up just converting the results here to TTNN, and then what we do is the only real like hardware accelerated versions that we actually like replace our CPU operations with is with these transpose matmuls and softmaxes. But what ends up happening anyway is that we're moving things from from CPU memory to the device memory all the time with these types of operations here, like this from torch here, and then when we're done, going back to torch from the device itself. So two big things going on here is that we always do this recompute that we would have already done on CPU anyway. And then we're moving things back and forth between CPU and device, which goes through the PCI Express bus, right? Even though it is Gen 4 by 16, that's really only still about 32 gigabytes per second. Okay, we're not transferring that much data, but it's still not as fast as going from chip to memory, or DRAM in this case. So what can we do? Well, let's actually slowly optimize this. Let's slowly, but step for step, try to optimize our self-attention TTNN v2 to the point where we can try to shatter this 55-second time that CPU gets from this benchmark. Okay, so first things first, let's create a new title: self-attention TTNN optimized v2. Okay, so optimized self-attention TTNN v2. What? I just repeated the same thing. No, let's just do it this way. Optimize self-attention TTNN v2. Okay. Okay, so one thing I want to explore is basically the memory config. So let's add a title here. So memory config. Going back to our documentation, there is something called memory config. Now, if we look at not this one, this one. Okay, if we look at what memory config is, there are just basically three types. There's DRAM memory config. The buffer of the tensor is interleaved and stored in DRAM. L1 memory config. The buffer of the tensor is interleaved and is stored in the local cache of a core. And then there's a create sharded memory config. Is the buffer of the tensor is sharded, physically distributed, and currently the tensor can only be physically distributed across different cores L1. Okay. What I'm curious about is this one, TTNN L1 memory config. And let me show you something. So go to doc site again. Let's take a look at the card. Wormhole. Okay, so taking a look at the specs of the card again, the n150d, notice how that we have something called SRAM. That's actually the L1 cache for the core, the Tensix core themselves. And I believe that this 108 is divided across, I think it's a 1.5 meg or 1 meg. It's a little over 1 meg per Tensix core, maybe. Let's just do the math. 108 divided by 74, was it? Yeah, about 1.5-ish megs per core. So SRAM is faster than DRAM, even though this is GDDR6. That's pretty fast. What we want to try to do is we want to try to put some of that data inside L1 cache. So whenever we create tensors, we can actually place something in L1 cache through this memory. Where are we at? Did I just lose it? Wow. Yeah. Oh, yeah. Here. This memory config. Okay. So let's actually look at what that looks like in terms of program. So whenever we have a let's see, whenever we do a from torch or any other type of call, the API, some APIs will actually have something called a memory config. So you can actually specify manually the sorry, I just saw a squirrel. Um, memory, you can specify the exact place in memory where this tensor is going to live in. So writing this down, like from torch, for example, provides us that type of option. We can try that out by first opening the device again. Okay, so let's say we have a test TTNN tensor, and we can just do some sort of like random torch tensor, torch.randn. Let's make it a 256 by 128. Then let's make it a default 16 tensor. Layout will be tile layout, and then device will be sitting on the device, but memory config is going to be L1. Okay, and then let's just move that to back to CPU and see what we get and do a comparison. So test CPU would be ttnn.toTorch, would be test ttnn, and then let's just see what test CPU looks like. Ooh, that's not good. Why? Oh, I probably forgot to close the device earlier. Okay, that's okay. So let's import stuff here. Import ttnn. Import torch. Okay. Let's run that. Okay. So we get this normal tensor. Okay. How do we know that things are working? Well, we can also do trace. So import from ttnn.tracer, import trace and visualize. Okay, so we can do with trace. Okay, test ttnn, and then we need to set that environment variable to Dewey. So let's also do this import OS, and then let's just copy where are we at? Let's see, right here. Let's just copy this and then paste this here, and we just get rid of that. So import OS, we'll import everything here. We open our device, and then let's visualize. Let's visualize test ttnn now that we know that it works. So visualize test ttnn. Okay. Oops. It's not supported in fast runtime mode. Is it because things I need to restart again? Let's see. Okay. Oh, I probably needed to close the device separately. Let's do that. Split cell. Okay, cool. All right. So our tensor, because we specified memory config to be L1, we have an L1 memory config here. Okay, so that means this tensor lives in L1. So already that could provide us with a decent performance uplift. Another thing we can do is we can also, instead of using Torch to compute those weights, remember we had in the forward pass, we had passed the input to W query, W keys, W whatever. Instead, we can just use the API available from TTNN to compute those linear transformations. So TTNN has linear. TTNN.linear is basically doing a forward pass on W query, W values, and W weights, or sorry, W query, W key, W values are. Except that linear is going to need the weight tensor from those W underscore attributes in the self-attention v2 class, because internally these W query and W let's see here, yeah, these W queries, W keys, W values, they aren't real raw tensors. They are linear modules that we need to access. We need to get those weights, and so we can do that by I think just accessing its own internal dot weight property, which will get us back the specific tensor associated with it. Okay, so that is pretty constant until you have to update the weights through training, but we'll worry about that later. So the first tensor is going to be your in this case your input. Your second tensor is going to be the weight of that W linear module from Torch, and then you can just use transpose B to perform that transpose, and basically it'll take care of the linear transformation for you. You can also specify the memory config, so where it's going to live at, and then also another one is core grid. And core grid is how you're going to lay out your tensor in terms of using multiple cores. So this is as much as I know. In the documentation for TTNN, there is something called tutorials matmul. Okay, inside here there is something that says initialize tensors, multiply tensors. Okay, matrix multiply tensor A and B by using a more performant config. Okay, so here is a tutorial on how to make things go faster, and one of the things they use was L1 memory config. But another thing that they do is use a core grid. Okay, and it says enjoy a massive speed up on the subsequent runs. So we could do that too by passing that into our linear transformation. And actually, fundamentally, linear transformations are also matmuls too. So if we look at matmul, we also have the same type of inputs available with memory config and core grid. So let's leverage that too. Okay. So, what else can we do? Yeah, let's do that for now. So let's start writing our class. I can't see anymore. It's getting bright. Okay. All right. So let's write our class. So class self attention TTNN optimized v2. It's getting long. And then dot module, still a PyTorch module. We want to treat it just as such. Def init takes in the d in, d out. Make sure we have self here. And then we'll also provide the device. Okay. Now I am just going to copy and paste the other one. here. No, not here. So let's just get all of this, and then we'll go from there. Okay. Okay, so what's going to be different this time is that we are going to create TTNN versions of the W query, the W key, and the W value. Not directly on them themselves, just the weights of it. And since these things don't have biases or bias values, we don't need to create the bias TTN. We do not need to create the bias TTNN versions. So we'll just store those TTNN tensors in this instance itself, and then we can always update them later. In this case, since we're focused on forward passes, we don't really need to update them. We haven't been we're not in training mode yet, so yeah. So let's create some properties. W query TTNN, for instance. We can just create TTNN from torch, and that is just going to take in self.wQuery dot weight. Okay, so we need to access the raw weight tensor, and then same thing. D type is going to be ttnn.bfloat16. Layout is going to be ttnn.tile layout, and let's also put that into the device, and then let's specify it to live in L1. Okay, L1 memory config. And so we're going to do this for the other two tensors here. So self.w key ttnn ttnn.fromTorch self.w key wkey.weight d type ttnn.bfloat16. Whoa, what's going on my keyboard? What's going on? Hello? Okay, that's weird. Anyway, layout ttnn.tile layout, device self.device, memory config is ttnn.l1 memory config, and then we'll close that. And then we'll create one for w value. So w value ttnn.fromTorch self.w value.weight, and then lazy now, so I'll just copy paste that here. Okay, so we created TTNN versions of these three here, so that we don't always have to recompute on every forward pass. And let's add a minor optimization for the scalar value. So we could do self.scalar is 1 over, so that's the divide part. We'll just do a multiply this time. D out 0.5. Okay, D out is just basically the same thing as our the keys dot shape -1. Okay, and then let's write our forward pass. Okay, so now it gets tricky because we want to avoid this operation here. So let's go back up. We want to avoid doing this again in the forward pass. This is no good. Don't do this. This is repeating work, right? So we want to convert our x to be a Tenstorrent TTNN tensor, and then call TTNN linear on x, in this case xttnn, and then our equivalent w query, w key, w value TTNN tensors that we had created in the constructor. Okay, so first things first, we create an xttnn Tenstorrent tensor. So it's just ttnn.fromTorch, pass an x, d type is ttnn.value b float 16 layout ttnn dot what is it, tile layout, and then device is self.device. Okay, we don't want to put an L1 memory config because I feel like there's no point. It's always going to just, you know, these things happen so often. I don't think it deserves to just live there. I think of it as like cache. So now we need to compute the queries, the values, and the keys that we would have gotten when we performed the linear transformation. But this time, let's use ttnn.linear to get that. So we're not going to do any of those torch transformations again. We're going to do it directly on the Tenstorrent accelerator. So queries ttnn, for example, would look like ttnn.linear. Okay. X ttnn, so that's the input. And then we'll actually access the weights of the query. So query ttnn. And then we'll specify the transpose b, because that's what a linear transformation looks like. It's just basically take this weights here, transpose that, and then core grid. So we're not going to use the L1 memory config. Instead, we're going to specify the core grid. So ttnn.core grid. Specify, I think, the y and the x. In this case, how they did it was, yeah, specify yx 8 and 8. Let's just go with 8 and 8 for now. Core grid 8, and then x is 8. Okay, and then we'll do that same thing for all the other tensors that we want to perform the transformation on. So values will be, you know, ttnn linear, and then keys will also be ttnn linear, and then do we do the transpose? No, we don't, not yet. Okay, so I'll copy that, and then I'll change this to values, and this one will use values. Okay, and then we'll finally have keys. And this will be keys. Okay, so we'll have those transformations there, and then let's compute the attention scores now. So by now we should kind of know the pattern. Attention scores ttnn is going to be a mapmul against the queries and the transpose of the keys ttnn. So this case it's queries ttnn mapmul ttnn.permute. We want to just permute right away. Keys ttnn. Oops. And then shape 10, and then specify a core grid. ttnn.core grid. Y equals 8, x equals 8, and then we'll take that, then we'll normalize all that. So it's going to be ATTN scores, not normalized, scaled. Okay. Think. So our scalar was 1 over whatever, this thing here. So instead of dividing, we're just going to multiply straight up. So it's going to be attention scores ttnn times self.scalar, like that. Then we can get the attention weights ttnn, which is going to be the ttnn softmax of attention score scaled against the last dimension. And then I think it's just mapmul on the attention weights and the values again. So context vex ttnn is ttnn.mapmul, and this is going to be the interesting one, right? So it's going to be attention weights ttnn against values ttnn. Core grid, which is, I can just probably copy and paste here. Okay, core grid with 8 and 8, and then finally, to be fair, let's copy that back over to the CPU, context vex to torch, context vex ttnn, and then let's return context vex, and then it's not defined. Oh, because we had reset our notebook. Okay, let me run it everything through one time just for, you know, consistency. And then for any of the long stuff, let's see. The benchmark stuff, I could probably skip. Oh, I do need to create these things, so that only takes 5 seconds. And then we can keep all that here. This one is no problem at this point. Yeah, let's just define that. Okay, so this should work now. Great. Okay, so we have our optimized self-attention TTNN version module thing. And basically, again, it's what we would have had in our regular torch module, but now we also convert these, we pre-convert those weights, okay, directly. We don't need the bias values to TTNN, so we just reuse them in the forward pass as such here. And so it just becomes a direct TTNN linear call to get the same effect as we would in the torch version. So now we're no longer like pre-computing, or we're no longer like computing the CPU version again and then converting that to TTNN. Instead, we're using our TTNN tensors and using those to get the results right away. And we also use core grid, and some of this stuff is in L1 memory. And we just do our map moles again using core grid. Finally, take the result of whatever we have in our device and move it back to CPU. Okay, so let's write our benchmark code again. So torch.manual seed 789, then torch.set torch.manual seed, then timer is going to be reset, so we just do timer.reset, then timer.start, and then timer dot stop. I'm not gonna fall for it. Then we want to return or at least display the elapsed time in milliseconds. Now I'm gonna try to be smart about this. I'm going to define our device and open it. And I'm going to have another cell down here that will close it manually. So TNN. Okay. And then within this, let's do SA TTNN v2. Wait, let's say TTNN opt v2 self attention TTNN optimized not DN 2048 device, and then for tensor in torch tensors, which we should already have, let's do the same thing we did in all the other ones. Just assign result unnecessarily, I guess, and then just after that. Okay. There's one thing that Tenstorrent also suggests to do when you first open the device is that if you do repeated operations, you want to enable something called program cache. So that'll do that. But not true, device. So we want to enable program cache on the device, and then we'll run all this. And we'll just see how fast we can go. So again, I'm gonna run it twice, so we'll report back. So let's see what it gets on the first time though. Hopefully my code is okay. It's not okay. Why? Why? Let's see. Self-determinant has no attribute, W values, TT, and N. Okay, let's close the device so that I don't crash the kernel, and then see what's up. See what is up. I pluralize things again. So here. Okay, let's see how that goes. Open the device, run this thing, and is it going? It looks like it's going. Okay, we'll wait a little. I wonder if this thing is doing any work. We should quit. Do it again. Yeah, 32 watts in use. Not sure if it's going any faster. Okay, I'm not sure what happened earlier, but something happened. I'm gonna rerun it again. It just kept going and going to the point where I'm like, I don't think this is reasonable. Anyway, it's done. Okay, so this one took 9 seconds. Okay, so what happens if we run it again? So 8.7 seconds. So now to process the same amount of tensors with hardware as we did with CPU. So let's go back to the CPU result. CPU gave us 55 seconds. Our crappy version on TTNN gave us 69 seconds. But our optimized version is 8.7 seconds. That is pretty cool. Now if we close the device and do it again, it's most likely going to take a while. Okay. Actually, I still think that's pretty good. 8.9. Okay. Now, I am curious. I'm curious that if, let's say, you go, why don't we just put everything on L1 cache? Well, there's two concerns that I have in that you may not fit everything in L1 cache and you might crash because of that. Or, like, does it make sense? Does it make sense to put certain things on L1 memory? Will we even get any speed up? Actually, let's try to find that out. Let's see what happens when we put something. We'll put all these tensors here in L1 memory and see if we actually get any performance benefits. So memory config will be ttnn.l1 memory config. Actually, let's put that here at the end. Okay, and let's define it. Yeah, let's do that. Forward pass. Do we have anything that allows us to put memory config inside linear? Let's see. Yes, we can. So let's do it. For education. So, oops. I don't know why this is doing this, but I'm used to actually having it work. Okay. So let's like spam L1 memory config on all of these. And let's also do the same thing here too. Let me just type it manually. Okay. And finally this one. Doesn't make a difference. Okay, so we're the TTNN. Okay, we forgot a comma on line 48 somewhere here. Okay, doesn't make a difference. Doesn't make a difference if we just put everything in L1. Okay. Can't remember our device is already open, but let's just do it. So, do we get any performance benefits? So far, 9.6. Let's do it again, because we're running it twice. So 8.2. So not really. You don't really get any huge wins from doing that. So that's why it makes more sense to just kind of be mindful about where you decide to do that. So just wanted to show you that. Cool. So if you took this optimization really serious, you can, let's try to do it again. So just clean version. We can literally get, what is it? 55 divided by 8 is what? 8.2. Let's see. Let's say 8.5. 55 divided by 8.5. It's basically a 6.47 x speed boost on our hardware compared to CPU. When it comes to power consumption, I kind of want to do this. Okay, I'm going to bend down and look at my kilovolt. I'm going to get this computer idle, and then we're going to start the CPU benchmark. And after that, we're going to measure, like we're going to get the starting number, and then we're going to run the benchmark, and I'm going to look at the power consumption, and we'll take the delta. Okay, so let's do that. So let's run the CPU benchmark again. Okay. Where is it? Did I go too far? I went too far. Okay, this one. Okay, so I'm going to shut off the camera because I don't want you to laugh at me. Okay, and I'm going to just see what the power consumption is right now, and I'll write this. I think I'll write this down here. So start power consumption. How much am I drawing? At least my server, my development computer. Okay. It says 138 watts right now. Okay. During benchmark. Okay, I'm going to run the benchmark, and then I'm going to see how much power it uses. So 1, 2, 3, go. Okay, so I'm going to bend down again. Wow, we're seeing 222, and I saw a jump to 400 at some point. But it's holding at 222. Yeah. I'm going to say 222 because it was only like 400 watts for a second or two. I think that's probably like a turbo boost. Two 223. Okay, let's call it 223. Okay. So 223 watts. Okay. Now let's look at the optimized version. Fair, make it fair. Okay, so the optimized version here, let's just note this down. Start power consumption. Okay, so let's I'm gonna go down again. Let's record what we have here. Okay, this time at 139 watts. Okay, end power or during power consumption. Okay, and let's run the benchmark again and see what happens. Okay, so ready, set, go. Okay. Hard to tell. Looks like it's 200. Looks like it's about 200. Yeah. Oh. So 200. Let me run it one more time. Ready, set, go. 230. About 200 to 230. Let's say let's call it 215 for fairness. Okay. So 215. So basically we had a net or a delta. So we open up a calculator. Can we have K-calc? Okay. So we had 215. Is that what I just said? Yeah, 215 minus 139. So 76 watts extra. And the CPU version. Oh, it looks close. Delta. I would say they're the same then. $85. My CPU is a 65 watt too, so I'm pretty surprised that it cranked that high. Okay. So 85, 76, I would say like there's some error there because this is like going up and down. What we're really noticing here is that for around the same power consumption, having this piece of hardware is amazing in that you can get like a 6 to 7x speed up. It's like 6.47 whatever x, right? So you can get that much speed up by using close to the same amount of power. I think that's amazing. So yeah, that's the video pretty much. I wanted to show you not only to make progress in this notebook, but also show you the difference in why it makes sense to have hardware acceleration, specifically with Tenstorrent hardware versus trying to do all this just using CPU. And yeah, the power consumption here, I would say maybe even is better than a GPU for the same amount of teraflops. So definitely a more efficient piece of hardware. I think that's it for now. This video has gone way too long, but I hope it was interesting, more interesting than the other videos of recent. And I hope it motivates you to go beyond the GPU and the CPU. So, thanks.